Welcome to this video on using servos on your model railway. Now, I'm going to do this as a series because we're going to look at a number of steps, not just the code to control the servo itself, but also how we then send those controls, whether you want to use a button, DCC, or various other systems. So we're going to look at different ways to control the servos. But today we're just going to start off with the basics of how to install the servo and set them up. So here we have a couple of common servos. We've got the ones that tend to come in the starter kits for Arduinos, an SG90, and here we have an MG90 servo. Now the difference between these, apart from the color, these ones tend to have metal gears, these have got plastic gears, but they tend to work equally as well. My projects tend to use the MG90 as I think they will probably last a little bit longer under stress. And here we have a turnout that is being moved by a servo. So turning the track over, obviously this is just a small sort of sample area. You can see that I have got a servo mount. It's one of these, and I'll show you where you can download the files to 3D print these. And as you can see, it's just the servo at the moment. It's flicking backwards and forwards, and that in turn is controlling the turnout. Now I also have here one of my uncouplers. This is for controlling KD couplings. It uses a couple of magnets that are lifted up into this base. The base sits under the track, but once again, when we turn it over, you can see that it is a servo that is going to control the unit. Now, for those of you who are wondering, obviously the track might look a little bit odd to some of you. The sleeper spacing is a bit odd. It's not HO, it's not OO, it is O16.5 or 7mm narrow gauge. So the turnout is exactly the same as a sort of an HO or a 001, but obviously the spacers are spaced slightly differently and obviously a different scale because it's for narrow gauge. But all of this will work with 00 or HO without any problems, and to be honest, the servo controllers for the turnouts should work with N gauge as well, or even other gauges. Now, as always, below the video you will find a link to the Digital Town website, and that link will take you to this section. Obviously we have the circuit diagram for the code that we're going to get involved with today. This is a little project to help you set servos up, whether it's for a crossing, a turnout, or for an uncoupler. You can use the same unit to do that, and we've got an optional screen that we're going to use. Rather than teaching you to program the Arduino if you're new to it, I've put some links to some lessons. Now, there is a series on the Digital Town site that goes right through the basics of learning to program the Arduino. So any code that I'm using in here, there will be a reference to some links so you can go into greater detail if you get lost. And also there are the links for the turnout, the servo mount, and the KD uncoupler if you want to sort of 3D print these up for yourselves. Just so you know, they're 3D printed. I did them on a very basic Ender 3. So basically any 3D printer you've got should be able to print those up. So that's what we're going to look at today. We're going to start with the basics of using a servo and some of the issues that you can come across with servos. So let's start with the back of my layout, or the underside of my layout. So if we zoom in a bit here, you can see that I have got a servo, another servo, yet another servo, and one down here. And as you can see, these are on the 3D printed turnout mounts. So these are controlling my turnouts, and then down here I've got another unit being put in. This is one of the uncouplers, and you can see I've just cut the hole here to put another uncoupler in there. I'm showing you the underside of the layout. It's probably not the prettiest, but This is pretty standard of what you will find under a lot of people's layouts, And the reason I'm going to show you this is just to show you some of the issues that can come with using servos, because servos have one little feature to them that can have a problem with model railways. So going back to the webcam, just taking a look at this servo, you can see that the connector has 3 wires. On this one there is a brown, a red and an orange. Now the brown is the ground, the red is 5 volts DC, and the orange takes what is called a PWM signal, pulse width modulation. And this is the method, if you like, the signal that's sent to tell the servo which angle to turn to. Now the DC, the 5 volt, and the ground, obviously that's just a normal sort of on off type, you know, it is the power is on or the power is off. But the PWM signal is quite a weak signal, and I'm just going to show you an issue with that, and it's quite important for how you install your servos on your layout. So pulse width modulation, what is it? Well, basically the servo is checking for a signal that is sent, and this signal has a duration. It's sent once every 20 milliseconds, and if the signal is 1 millisecond long, so this line when it's at the bottom here, that means that 0 volts are going down the orange cable, the PWM. It then raises up to, we'll say 5 volts, but if you're using an ESP-32, you can send 3.3 volts, it'll be fine. So you've got 0 and then your high signal, which we'll call 5 volts for now, and that is going to last for 1 millisecond. And if that pulse lasts for 1 millisecond, the servo sets itself to an angle of 0. Now, if we have the pulse of 1.5 milliseconds, it's going to go to an angle of about 90 degrees. 2 milliseconds is going to go to 180 degrees. These are slightly rough figures. They can be slightly out depending on the brand of servo, but it's a pretty good average for you to get. And obviously any value between 2 and 1 milliseconds will create the appropriate angle of the servo between the 0 and 180. In fact, it should be 0 and 179 to be absolutely exact. Now that means when you look at some libraries, things like the Arduino servo library, you put in an angle and it tends to be from 0 to 179, but the servo is actually capable of turning very smoothly to basically any angle. So you could have 90.23 degrees or something like that if you wanted. But this is going on every 20 milliseconds, and these signals are going out every 1 to 2 milliseconds. Now, don't worry, there's no homework on this, but I'm showing you this for a very good reason, as you'll see in the next slide. So here we go, 20 milliseconds. What is that? That's 20 thousandths of a second. But 20 milliseconds also happens to equate to 50 hertz. Now, those of us who live in the UK, our power supply is 230 volts or 220 volts, whatever it is these days, at 50 hertz. Obviously in the USA, I believe yours is 60 hertz, but you'll notice that these figures are going to be very, very close to the 20 milliseconds. The other thing with DCC, you know, for those of you using DCC, DCC is a signal that is alternating backwards and forwards. It's very similar to a PWM pulse, and it's firing off at, if you like, 1 millisecond is 1 kilohertz, and DCC signals are firing off at 5 to 9 kilohertz. So that means that they are switching on and off, or in DCC signals, they are going opposite very, very quickly. Now, this is important when it comes to the underside of your layout and the way that you set your servos up. So coming back to the underside of my layout, just so you can understand my wiring colors, red is, I'm on a DCC layout, so red is one side of the DCC signal and the black is the other side of the DCC signal. White and white with a black stripe on my layout is 5 volts, and I've got a different system for 12 volts. Right, now what happens with these, as the signal alternates, it produces an electromagnetic field around it, and that can generate power just as if you spin a motor, and it will generate power at the outputs as if it is a generator. Now this is important when it comes to your wiring. Now my system, these are using a PCA 9685 board to drive the servos, but what I want you to look at is the way that the wiring is done. You'll notice that this connection here to the servo does its best to avoid anything to do with a DCC signal. And on this servo here, where I've had to cross a wire that has a DCC signal, you'll notice I've gone at 90 degrees so that I've minimized the amount of time that the servo cable is next to the DCC cable, and indeed this could be a mains electricity cable. The same thing applies. Now the reason is that these cables can produce a small electromagnetic field that is enough to cause an interference with the PWM signal to the servo. So going back to our signal diagram, if I've got the servo set to 90 and it's at 1.5 milliseconds, if I had a slight interference that caused this signal just to stay high a little bit longer, a fake signal coming from outside, obviously that means if that goes to 1.55, then the servo is going to move. If that outside interference then stops, the servo is going to go back to 1.5. Now this is important because one of the issues you often have with people with their model railways is you get what's often called servo chatter, where the servo is moving very slightly, and one of the reasons for this is to do with this interference. So to prevent crosstalk, it's best to avoid the servo cables running alongside the DCC cables. And I'll show you a typical example. This is what I used to do in the olden days. This is my uncoupler, and I used to run the cables alongside the DCC cables, and obviously I'd put them under the clip so everything looked really nice, tidy and pretty on the underside of the baseboard. And then I'd wonder why this servo kept sort of flicking backwards and forwards. And it all came down to the fact of this thing called crosstalk. So to avoid the crosstalk, try and keep, basically you're trying to keep the orange as far away as you can from the red and the black from the DCC signals, or an AC signal if you are using a mains, or I believe, is it Marklin or something, actually uses AC to power some of the trains. So just remember that when you're trying to use your servos. So coming back to our diagram, what we now realize is that we need to send a PWM signal to control the turnout. Now unfortunately that means we can't just use an on-off switch. We can't just turn the power on or off. This signal has to be generated, and to do that we need some kind of controller. So what I'm going to do today is start to look at how that can be done and some of your options. Now you would think, because I do tutorials on using the Arduino and the ESP32, that I would say that that is the best solution. And in some ways I'd say it is, but there are alternatives that you need to be aware of. Now this is a unit by a company called Kitronic. Their website is kitronic.co.uk, and this is a servo controller. The servo goes on here, just plugs in here, and you press the button to move the servo in one direction, you press it again to move in the other direction. You feed in 5 volts and a ground, and here you have a tiny potentiometer that you turn with a screwdriver, and that will control the movement either side of the center mark, if you like, the 90-degree point that the unit will move to. Now, as you can see, looking at the pricing on the right, they're sort of what, £4.62, and I imagine there will be some kind of delivery charge on top of that. There are other options. Let's go to AliExpress, and well, how much is this one going to cost? This unit is it's going to cost £2 plus shipping. Obviously, better to buy a few of these if you want them. And the advantage of this particular unit is, once again, there is a button. This one has 2 potentiometers, and this one controls the range, so if you like, the left-right movement, but you also have a second potentiometer that you can then use to adjust the speed at which the servo moves. So again, very, very simple to use and ideal for controlling servos, with one problem for both of these units, and that is the fact that the adjustment range is either side of center. Now, with the units that I've got on my desk at the moment, let's just think about moving those either side of center. Going back to the workbench, we have my servo that is moving my turnout. Now, the way I build these is, obviously, I drill a hole through the plywood base and mount the servo unit underneath. Now, obviously, I took great care in trying to get this servo centered. However, I've never ever managed to get one centered correctly. Now, the problem is, and this one's quite good, in one direction it has to move 21 degrees. In the other direction, it has to move 24 degrees. Now, that means that if I use one of those units where it's, if you like, a set distance over center, in one direction, the servo is going to overpressure, and that will cause, again, a very slight chattering noise as the servo tries to move a distance that it cannot move to. So if you're going to use one of these sort of units that requires you to set the distance either side of center, you are going to have to be very accurate in the way that you set the unit up underneath. And let's be honest, if you look at the way I've set this thing up, let's be honest, I just drilled a couple of holes and did my best. Now, in the case of the uncoupling unit, what I've done now is push the servo down in its, if you like, the position where the uncoupling will take place. With this one, it's a little bit easier to use one of those units that's either side of center, because although it's quite a long travel, it'll then flick back up here somewhere for the opposite position, and that will allow the flap to fall back and the magnets to, if you like, stop uncoupling things. So a unit like this will tend to work better with something that uses a unit that moves something either side of a center position, but in general it is easier if you can adjust the exact angles for yourself, and that's what we're going to look at today. Now, one other issue, of course, when you're looking at these units and the way that they work, is they are quite small units. I'm sure there is a way somehow to unsolder this switch or put your own connections on to somehow extend the lead, but otherwise you're going to finish up with a situation where you've got to have this unit pretty close to the servo, and sometimes, especially in a model railway situation, the control panel can finish up being a long distance from the actual unit, especially if you're using a turnout. With an uncoupler, you may be a little bit closer to the action so you can see what's going on. But again, it's just one of those things to be aware of. There are units out there that will do what you want, sort of as a off-the-shelf item, but they still may need some modifications and they have their limitations. So that is the first option, is obviously just to buy an off-the-shelf unit. But now we're going to look at how to build our own using an Arduino. So this is the project that we're going to build today, and it's just a simple potentiometer down here on the front, and by turning it I can adjust the turnout, and you can see that on the readout I can see the servo's position. Now this is important because when you get these servos, when they arrive, you take them out of the packet and you don't actually know at that point what position this servo is in. Is it at 90 degrees? Is it at sort of 130 degrees? You just don't know, and that's important for when you're going to put the connectors on the top for any type of project. So this is, if you like, a servo setting project, and it would allow you, obviously I'm using it on a turnout that I've already set up, and I set mine to 90 before I installed it. However, if it was a brand new servo, I could very quickly just turn it to a position of 90, and I would then know to install the little hat on it correctly. So the components that we have here, obviously there is a servo, which obviously you can't see because it's underneath the turnout. I'm going to use an Arduino Uno today because it's a starter project, and an Uno is a great unit to use to learn on. We have a potentiometer here. This one is a 10K, but you could use a 1K. It really doesn't matter on the size of the potentiometer. I've got an I2C display here. Now that is optional. You don't need that on this project. You can read the values on the serial monitor. However, if you want to build a little handheld unit that you can take out to the layout, unless you've got a laptop available, which I'll be honest is how I tend to do mine, then it might be easier to attach a screen. One other thing to notice, this is a power supply to the breadboard. With an Arduino, it is possible to power one servo, but any more than one servo, and there's basically the Uno doesn't have enough oomph to do it. So this unit is supplying 5 volts to the rails. So all the Arduino is sending to the servo is the PWM signal. The actual power, the 5 volts, is being sent from this unit, and the same with the screen. That's getting its 5 volts from this rather than from the Arduino. Right, let's have a quick look at how this is set up on the circuit. All I've done is gone back to the Digital Town site and clicked on the circuit diagram so that I can get a larger version. So let's have a look at how this works. Now, as I said before, we have the breadboard power supply. I've got it set to 5 volts. As you can see, 5 volts are going up into the LCD screen. The ground is going up. With the potentiometer, just something to be aware of. Again, the Arduino ground must connect to the breadboard power supply ground. So all grounds are common. That is important. So the ground goes up to the potentiometer, but you'll notice that the red wire, which is 5 volts, connects to the Arduino 5 volts, not to the 5 volts off the power supply. Now this is important because the Arduino is measuring the resistance of the potentiometer using pin A0, and to do that it needs to make sure that what it is calling 5 volts is what the Arduino knows as 5 volts. If you plug the potentiometer into the power supply 5 volts, it might not be quite 5 volts and you will confuse the readings on the Arduino. So just make sure that that 5 volts from the potentiometer is connected directly to the Arduino. As I said before, the grey wire, the center wire off the potentiometer, is going to analog pin A0. If you're using the screen, and that's optional, you can follow the circuit diagram and you can see that there is an SDA and an SCL pin, and they connect to pins A4 and A5. And finally, we have our servo. Now the servo, again, the 5 volts is coming from the power supply. The ground is connected to the power supply, but also to the Arduino. And finally, we have the orange, which is connected in this example to pin 8. So when it comes to writing the code, obviously we have the Arduino IDE. And once again, if you go onto the Digital Town site, let's just flick to the code is available for download. Just click on the link. Also, while we're on the site, obviously there are the analog read, which is for the potentiometer. We've got a lesson on servos, obviously for our servo, and a separate lesson on the LCD screen. Now this is a specific screen. It is the I2C version of this screen, so it's worth checking out lesson 17 for more details on the screen. Right, let's get back to the code. So this first sketch is a very, very simple sketch, and all it's going to do is literally move the servo 3 times. That's it, nothing fancy, and this is what I would call a connection check sketch. And the reason for that is quite simple. If we go over to the webcam, one of the problems with all Arduino projects, especially when you're using a breadboard, is have you got all the connections not only plugged into the right positions, but also are they all correct? Has something flicked out and come loose? So this first sketch will literally test if the connection to the servo is correct. So we are going to include the servo library. We're going to create a servo object. I've called it servo1. Now the reason I've called it servo1 is if this is a model railway project, you may want to be connecting your Arduino directly to the servos. Again, there's 2 ways. There's what's called a PCA9685 servo driver board, which is very common when using servos. It's what I tend to use. So the Arduino would talk to the driver board, which talks to the servo, or you can talk directly to the servo from the Arduino. The choice is yours. However, this time I'm going to call it servo1 because obviously if I was going to have a number of servos, it would be servo2, servo3, servo4 would be included as well. Servo1 is on pin 8 of the Arduino. I'm then going to start the serial monitor and print out just the title of the sketch, servo1. We then attach the servo. Now, because I have called my servo servo1, that is what we would call the servo object. If I want to do anything with servo1, I have to go servo1 dot attach. If I want to move the servo, servo1 dot write. So that is saying I want to do an attach command or a write command, and that command is going to be to servo1. If I added servo2, servo3, servo4, I would have to go servo2 dot attach, servo1 2 dot write. So that is how if you have different numbers of servos, you can control lots of them simultaneously. Now the command to attach means that servo1 pin, which is pin 8, is the pin that is going to be receiving the PWM signal. So that, if you like, is starting the system up to control servo1. Now, I hate using delay, and you will find that when I write code, we do not use delay in the loop because it's a very bad idea, especially when you get to more complex projects. But within the setup for a small test like this, it's going to be acceptable. So all we're going to do is we're going to serial print the angle to the serial monitor. We're then going to send the servo to that angle. Going to wait 2 seconds. Then I'm going to send it to 10 degrees, obviously serial monitor, send the servo, and then wait 2 seconds. And then finally, I'm going to send the servo to its center position. Now, this is just a very quick sketch. And if you wanted to set a load of servos very quickly to their center position, this is a good way to start before you can, if you like, attach the servo horns. So let's get this thing uploaded and running. So the code is uploaded. I'm just going to start the serial monitor and let's see what it does. So it's going to move to 170, 10, and finally it finishes at 90. So at that point, I now know that the servo is connected correctly. So let's move on to the next sketch. So this next sketch is going to allow us to control the servo position. And the only thing is with this one, it's not going to use the screen. So if you don't need to use the screen, you just need to use this bit of code and you'll be fine. So once again, we're going to include the servo library. I've set up my servo 1. It's going to be on pin 8. And I am going to use the potentiometer pin is going to be pin A0. Now, you may notice I use const int. Sometimes you'll see it just as int. Const just means that the variable is write protected. So very often with a variable, you'll be adding stuff to it, subtracting stuff from it. Once it's got a const in front of it, it's always going to be 8. It's never going to change. And obviously it's a servo pin. It's not going to change. I've started the serial monitor and sent out servo setter version 1 just as a piece of text, so I know it's correct. And once again, I've attached the servo. Now what we're going to do is in the main loop, I've got 2 variables, the potentiometer value and the servo angle. And to get the potentiometer value, we're just going to do an analog read on the potentiometer pin, and then I'm going to serial print that out. That will prove that, if you like, the connection to the potentiometer is correct. So now that that's uploaded, we can see the potentiometer value going across on the left-hand side. And the test of this is to turn it all the way to one direction. You should get a 0. Turn it all the way to the other end of the scale, and the value should be 1023, because the Arduino will work on a value between 0 and 1023. If you do not get a value of 1023, check your circuit diagram and make sure that the potentiometer's positive, that's the red wire, is plugged into the Arduino 5 volts and not the breadboard power supply. Now, once we have the potentiometer wired correctly, we're just going to look at how to work out the servo angle and indeed set it. Let's just uncomment these lines. The first item we're going to use is the map function. Now, map takes a range of values and puts them onto another range of values. So in our case, the potentiometer has a range of 0 to 1023, and the servo has a value of 0 to 179. So the map value, if we take the potentiometer value, which is a value between 0 and 1023, it will work out the equivalent position in the range of numbers between 0 and 179. So we're going to serial print. We'll just change that to just serial print now, the potentiometer value. We're going to then just put a sort of something, a spacer in between, and then I'm going to put the servo angle, and at the same time we're going to move the servo to that angle. So the code is uploaded, and you can see that we have the potentiometer value on the left. We then have the angle that the servo is at on the right. So at the moment this is at 124 degrees. Now when I start to turn the potentiometer, what I'm doing to try and, if you like, get the range of the servo movement, as I turn this, I'm listening, and I want the point blade to move over into its correct position. But if I move it too far, it probably doesn't pick up on the mic, but the servo starts to make some sort of odd noises where it's sort of being overstretched. So the same when we come back the other way, I don't want any sort of background noise coming off this servo, but I want to make sure that the point blade is in a really nice position. And obviously on your layout, if you just sort of move it backwards and forwards, you will find the correct position for the throw either side of 90 for your turnout. So finally, we're going to add the screen in. Now the screen uses I2C in the example that I am using. So if you're ordering a screen, as you can see, they're not particularly expensive. This one's on AliExpress, but the important thing here is that the screen has this unit on the back, that sort of black board that is attached to the back of the screen. That is what's called an I2C backpack, and it means that you can run the screen basically off 4 connections rather than having to use the conventional way where you would be connecting most of these pins to your Arduino. So I am using an LCD 1602 I2C version of the 16:2 LCD display, just so you make sure you get the right one. So once you've got the correct screen, then we just include, obviously as before, servo, create a servo object. Now I'm going to include the wire library and the liquid crystal underscore I2C library. Again, if you're getting stuck on this sort of bit, there is that extra tutorial on the Digital Town site specifically on this screen, so I'm not going to go into it in great detail. Set up your screen, start the setup. We start the wire library. We then start the LCD screen. This is very similar to the idea of attaching the servo. This is, if you like, start your engines for the LCD. We're going to turn on the backlight, and I'm going to set the cursor to position 0, 0. That is top left on the top line. And we are then going to print servo position. I've then done as before, attach the servo, and then down here the only addition is I've added a variable servo string. Just as before, we're going to get the potentiometer value, calculate the servo angle, do our serial print, and, if you like, move our servo to its position. And then I am going to create a servo string. This is using a string padding function. Now again, I'm not going to go into this in detail because it's actually on that servo lesson, so take a look at that one if you want to know how it works. But all it finishes up doing is sending the servo position to the screen, as you will see as we upload the code. So now, just as before, you can see on the serial monitor that I have the position, but at the same time I now have the position on the screen, which makes it a lot easier if I've got to keep moving one servo to another. So if I was going to set a lot of servos, I would tend to build something like this and just go out in my garage and do them all in one go. So once you now know, if you like, the optimum position for the servos, you just jot down the number that's off the screen, and you will then know which values to put in the next sketch, where we will start to, if you like, control the servo with buttons or DCC. So as I've just said, we're going to do some lessons on controlling with DCC and buttons. I shall also do some using the NOW rail system. If there's any other way that you want to control servos, let me know and I'll see if I can fit that into the series. That's about it for now. So please, if you want to see more of the content, please click the like and subscribe, because it really does help the channel with the dreaded YouTube analytics. So thanks for watching, and I'll see you in the next video. Bye for now.